In the previous videos, you have known that definite integral geometrically is interpreted as the area under the curve. And in the previous page, you have read that there are actually steps, right, to do the calculations of the areas under the curve by constructing rectangles under the curve and then summing those areas. Okay, and approximately the sum of the areas of the rectangles is equal to the area under the curve. Now, if the width, the base of the rectangle uh, approaches 0, then the number of rectangles approaches infinity. All right. So for this lecture, we are going to talk about the Riemann sum as an application of the steps outlined in the previous page. Okay, to start this one, let us consider the same function, right? A function on the x and y coordinate plane. Okay, so this function y is equal to f of x as illustrated. So we want to get the area, or we want to solve for the area of this curve under the curve from point A, x is equal to A, to x is equal to B. And so the first step in calculating for the area is to create rectangles, right, by subdividing this interval into rectangles with equal base. Okay, so we are going to draw rectangles with equal bases. Right, so this one. Right, so the base of these rectangles are equal, the bases are equal, and let us denote the base delta x. Right, so let us consider a point, arbitrary point, somewhere here. We call this value of the point, the x value, zi. And if we try to extend this one, there is a corresponding y value for that point right there, and that value is f of z sub 1, or f of z sub I. Now, if you try to look at our representative rectangle, ito, what is the area of this one? So basically, the area is equal to the base times the height. We know that the base is delta x, right? The base is delta x, and the height is f of z sub I, right? So there are a lot of rectangles dito. Maraming rectangles. So to calculate for the total area, we need to sum the areas of the individual rectangles. Okay, so for the first rectangle, since pare-parehas naman yung bases nila, the first rectangle has an area of delta x, and let's try to look for any point, and that point is f of z sub 1, For the second rectangle, the area is delta x, f of z sub 2, and we can go on until the last rectangle. The area is f of delta x, f of z sub n, whatever that last rectangle is. Alright? So this summation, this sum of areas of rectangles, can actually be written in summation notation. Okay? And that summation notation is the sum of delta x, f of z sub I, where your I starts from 1 to the last rectangle n. Okay, so this is actually the formula for the Riemann sum. Okay, and what do we want to do here? We want that the area be equal to really to the actual area. And how do we do that? Kasi nung pagbalingin tayong siyempre no dadaktil dagiti rectangles, ano agpaypay tong area under the curve DJ, di ba? DJ discrepancy, the discrepancy between the true area and the total area of the rectangle. Malaki yung discrepancy. So we want the width or the base of the rectangle as small as possible. And to do that, we need to create many rectangles. The more rectangles we have, the better, di ba? So mas malapit sa katotohanan kapag mas marami yung rectangles. Okay, so we want the width of the rectangles to be infinitesimally small. Okay, and to do that, we need to take the limit of the sum. We need to take the limit of this sum as n approaches infinity, right? So we want n to be infinitely large, right? So dapat adu nga n, dapat adu nga rectangle tapno maalat ka dito nga area under the curve. And basically this one, the limit of the sum of the areas, is actually the definition of the indefinite integral. This is the integral. You can actually write this as the integral of f of x dx from A to B. Alright, so we shall have examples regarding this formula in the next video.